Alright, Joyce, we started by having them work through chain rule, and I was like, hey, why are we taking a whole day on the notes for the section if it's just chain rule? And they were like, working. And I was trying to get them to get to something a little bit weird, and they did right about here. So anyway, if you want to take about 10-15 minutes, work on homework up until about here, and then we're going to transition to notes. Notes.
No.
No, oh, I don't want that one.
Ooh, look at 51.
Oh, if you're gonna say hi, Joyce. Hi, Joyce.
There we go. You guys ready? To prepare you for 36 and 41 and beyond. 36 is weird because they gave you weird stuff. 41 is weird because, oh.
It's a lot of work.
I don't even know what 51's asking.
What's 41 asking?
41's asking the slope of the tangent line. No, the equation of the tangent line.
The equation of the tangent line to what?
Don't tell me that's
To the curve.
Is that a parametric curve?
Parametric
Oh.
curves?
Son of a-
What? That's awesome.
Kill me now.
Everyone say yay.
George, you got any bleach?
No, Miss D drank it all. Or she took it all, I should say. She didn't know if she drank it.
Oh no! Did you guys just see me get to where I needed to be?
Yes.
That was rough. Don't worry, I got this. Alright, we are in section 4.1, due on Monday.
Bless you.
Dun, dun, dun.
Thank you.
I wasn't sure if I was doing 4.1 alone or with 4.2, but we are definitely doing 4.1 alone. This is homework number 11, right?
10.
10. No.
Oh, 10? 9?
Definitely 10.
Definitely 10. Okay, we'll take that.
I mean, it's funny. The ironic thing is that you told us to do homework
It's
numbers at the
11.
beginning of class.
Wait,
It's
2.1.
11.
What?
Yeah. Unless you, wait, the test review counts as 1, right?
No.
No.
You should.
You guys are so silly. It's number 10. Ta-da!
So does the
Okay.
test review not count as a...
Question. What is the idea you guys teach me the chain rule with an example? Ready, set, go. What's the idea behind the chain rule?
Doing that
Not
without
necessarily.
doing that without having to expand the x to the 5th thing.
Yeah, without having to expand x cubed minus 17 to the 5th power. However, what's the big picture of what's going on in this example?
You're deriving
Product rule.
product rule too.
A product. Okay, thanks. Just checking. Deriving a product, right?
Yes, so.
So then when we go through, you guys just practice this quite a bit. What do we do?
You derive the first.
Derive the
times-
first.
This times the second.
Second D first.
It's either
Plus?
way. It's adding, so it's either way.
I know.
Plus derive the second one with chain rule, which would be 5x cubed minus 17 product to the 4th
Oh, second D
times 3x
first.
squared.
Oh, that's what he's doing though. Second D first and first D second.
Yeah, because it doesn't matter. It's adding.
As it matters, that's how we learned it.
And that's how we're comfortable.
But how do we take the derivative of the second one?
I just explained that.
No.
How?
5 times x cubed minus 17 quantity to the 4th times 2x squared.
3x.
3x squared. So I was confused. I always switch those two numbers. Freudian slip.
Well, I'm not sure if it's for you. Like that?
No.
And then
Yes.
Second D first plus first D second. Brought down the 5, multiplied by the chain rule, 3x squared, and then I have blah, blah, blah to the 4th. Now how do we simplify?
Carefully.
True. Come on, help me out,
Distribute.
my AP kids.
Distribute.
No.
Make x cubed minus 17 u.
Kind of.
Fours.
I wouldn't think of it as u though. I would just pull out x cubed minus 17 to the power of
Fours.
4.
Because we got...
Because I have shared factors. And then I would go ahead and keep what I have left, which would be negative 2 times x cubed. Gerardo, this is making it match because almost always they're factoring out these huge ones.
I thought you were asking how to make the entire problem simpler. Gotcha.
Oh, lo siento. Does that make sense?
Yeah.
I have no idea what you're doing actually.
I pulled out, because there's 4 of these. This is a making it match problem because they would not probably write this. They would not distribute it all. They would pull out common factors and simplify as much as possible. So there's 4 of these in common, pull out all 4, what's left? Negative 2 and 1 of those, what's left? 15x squared.
You did that on the summer packet, and I was just like, how did you get here?
Mm-hmm.
And when I finally figured it out,
It's a
I felt like
complicated
an idiot.
step. It's just making it match, and
Yeah.
it's what they love to do. So then we'd end up at the end of the day with negative 2x cubed plus 34 plus 15x squared minus 30x cubed, I believe. You guys can double check?
And then minus 2x cubed.
Exactly. So then we would have x cubed minus 17 to the 4th times negative 32x cubed plus 15x squared plus 34. At least at this point, we should be able to make it match. Maybe they would pull out a negative or something random. I doubt it. I think that would be appropriate. But question, where did the chain rule come in?
Maybe you derive the second part.
Yeah, when we brought down the 5, leaving the x cubed minus 17 the same, made it to the 4th power, and then what was this step right here? U prime for u equaling x cubed minus 17. Are we good?
Let me just check it. Yes. If it's a free response, can we just stick it to the man and leave that first one up?
Technically, yes.
What do you mean by technically yes?
Because
I'm
what
sorry.
if you have to reuse
Because
it?
if you need to use it or solve for zeros or do something with it, it might not be best to leave it that way. But I would say technically yes. So let's review real quick the chain rule in all of its different forms, and then maybe it'll help us on 36. So then coming back. Leibniz notation is probably more proper, would tell us, take the derivative of y with respect to u. If we're thinking about a composition of functions and u being the inside, we could take the derivative of y with respect to u, which would look like, take the derivative of the outside, function with respect to u, but we're not done, because guys, is dy du the same thing as dy dx?
No.
So then we need to consider the u, and consider the u prime, which we consider by saying take the derivative of u with respect to x. Now technically, the way that I have said to remind you is, hey look, they cancel out, you did it right. Is that technically what's going on here? No. There's actually a much more formal proof as to why we're able to do dy du times du dx. But as our book says, basically, you need to learn some more to be able to understand it. So anyway, that is the notation for what we're doing. Here's the shortcut way of showing it with f prime of u times u prime. And how would we show that in function notation?
F prime of g of x times g prime of x.
Bingo. So then in number 36, what do they tell you?
F of g of x. Find the derivative.
No. They tell you f of u, and then they tell you who u is, and then finally they tell you who x is, right? So if we were to take something like, I don't know, something simple, like number 34. Maybe it's not simple, but that's okay. Number 34, you guys still have your books open?
Mm-hmm.
Okay. So for example, for the exercises, number 34, our goal is basically to find the derivative with respect to x, but what do they tell me for who f of u is?
I get it.
F of u is?
A very nasty term.
Okay, does no one have their book?
I do, but
Is that it? Okay, and what does u, who is g of x, equal?
1 over
1 over
1 minus x.
And who do they want x to equal?
Negative 1.
What's the thing that we're definitely dealing with last?
Yeah, one.
Okay, we're not
Because
plugging
it just you make your life harder.
Well, we need to make sure that we take the derivative with respect to variables, not one single constant. True?
So we would take the derivative of the first, multiply by derivative of the second, and then plug it into x, right?
Basically.
Okay, cool.
So f prime of u is going to end up to be
f prime of u is 1.
1 over u squared, yeah?
Yeah.
But we've got a negative 1, that's a positive, and then subtract 1, negative 2. Who's u prime going to be?
U prime is
Oh, that's some chain rule loveliness.
If I can make it 1 minus x to the negative 1, does that help?
a lot.
I don't know if it helps a lot, but it could help. Bring down the negative 1,
Makes my life easier.
and that's going to be the negative 2, but then times u prime,
which is a negative 1.
it's going to be a positive, right? Hold on, wait, are we tracking? Bring down the negative 1, so negative 1 over 1 minus x squared to the negative 2. Times u prime, negative 1. Good? And then we have x equals 1. So how do we put it all together to get the dy dx?
Kind of just multiply it.
No.
Is d it's negative 1?
Thank you. That was close.
Also,
Huh.
isn't it negative 1 for u like,
But we brought down the negative 1, and then we had another negative 1, hence positive.
no, but for a u prime, don't you have to also multiply by negative 1 because it's 1 minus x?
Yes. But when we take the derivative, the negative 1 came down,
Okay, I think I got
then negative 2, then times u prime negative 1 times negative 1
Got it, okay,
became,
got it.
yeah.
it.
Without the u prime, we would have had still a negative.
Okay, it's
So we're gonna need f prime of u of negative 1 times u
Wait, can
prime
we
of
go
negative
fast?
1, right?
Can we not go that fast? Can we go f prime of u and then just u prime?
Yeah, we can do
And
that.
then we can plug in?
Is that better?
Yes.
And then wait?
yeah.
Ta-da.
I'm getting 1 minus x quantity squared over 1 minus x quantity squared.
I don't think that's right.
Because u is 1 over.
You should get 1 minus.
Because then, hold on, we're plugging in for f prime of u. It's
Mhm.
gonna be 1 over who?
1 over 1 minus x.
Should give you.
Yeah.
One over
So if
1
you
minus
if you
x
if you square
So 1
everything-
over, calm, thank you. So 1 over u squared, plugging in u, that'd be 1 over 1 minus x quantity squared times my u prime, which is 1 over 1 minus x quantity squared. Why is that weird?
Because then it flips up, f prime flips up, right, and then the 1 over 1 minus x quantity squared cancels.
Uh-huh.
So then we get,
Or we could look at it as, and then we end up being like, so do we even have to worry about at negative 1?
no,
Constant slope. But if we did have to worry about negative 1, we would still have x's remaining and we would plug in the negative 1 and be done.
yay.
Is that okay? So are we literally just using one of the descriptions of chain rule? Yes. They're just helping us out, kind of makes it a little bit more complicated.
So
But
they
that's
simplify it for us by making it more complicated.
No, they rewrite it for you. I don't know if it's simplifying per se, but they're
Because they-
rewriting it and giving you different details, which the AP loves to do. What if there's a 3-link chain, is how our book calls it, but what if there is an f of g of h of x?
What?
An f of g of h of x. What am I talking about? In pre-cal, we talked about something called decomposing functions. And figure out who is the innermost, who would be outside of that. And who would be So there are multiple different ways of finding this derivative. One way is just to understand how the chain rule works and follow it. Not forgetting any of the inner function primes, the u primes that are contained within. The other way is to actually think about it in terms of the definition where we take the derivative of the outside, keep the inside the same, times the derivative of the inside, keeping his inner function the same if necessary, times the derivative of the inside until finally we get to x prime, which is really just
X, no.
1. We finally get to there's no other inside besides an x, and the x prime is really just a 1, so then we stop. So we could go through and actually figure out who is f prime, who is g prime, who is h prime, and basically plug in a lot of stuff. Or we could try to use the process in the sense of thinking, let's work our way outside in. 1/3 power for a cubed root, right? So help me out. For the derivative, for dy dx, or f prime of x in this function. What's the outermost derivative that I'm taking?
X 1 over
Yeah.
X.
Bring down the 1/3. I have 17 minus cosine of 3x. I have remaining the negative 2/3 times. I've dealt with the outermost. We called it last year the matryoshkas. We dealt with the cubed root. Now we have to work our way in, but remember the chains are linked by multiplication. So now pretend that the cubed root is gone. We have 17 minus cosine of 3x. Derivative of 17 is 0. Derivative of negative cosine
Is
Positive sign.
is positive sine of 3x. So we've dealt with the cubed root. That was the first thing. We've dealt with the 17 minus cosine of 3x. What is our last thing to deal with? Derivative of 3x is 3. And if we keep on going, the derivative of x is 1 if we were to keep on going. We should always end with 1 and we're done. And then to write this nicer, it's not gonna be gorgeous, right? But I could go ahead and simplify my 3's, and I'd end up with sine of 3x all over, if we were to do it that way. Let's just say 17 minus cosine 3x. Can I just make it to the 2/3 and we'll just leave it? But it would be squared cube rooted if they decided that they wanted to show that notation. Dun, 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 dun. Okay, questions, are we okay?
So when you get to the sine part, you just take the derivative of sine, make 3x a u.
In essence, it's
And-
kind of like you're moving the
okay.
u along the way.
Okay, I get it.
Is that good? Okay. Now, what happens in number 41? We have more examples, but you guys did homework, we're done. Ah! What happens in 41?
We have to change it, but no.
Parametric curves.
You haven't taught us those yet.
Yes, we have. We talked about parametric equations.
Oh.
Remember? We
Yes,
spent the whole
for
time on parametric and polar, the very first quest that we had, quiz test. So parametric equations, let's review. Remember those are the x of t ones and the y of t ones? And remember that we're defining something in terms of its horizontal and vertical components separately, both dependent on the parameter time. We talked about how to eliminate the parameter, et cetera, et cetera. Here's the long story short. Does it make sense that dy dt could equal dy dx times dx dt based upon what we know about the chain rule?
Yes.
No.
It's the same thing, just
It's
different.
the same thing, but instead of starting with dy or y in terms of x, we start with y in terms of t, which it is, right? So instead of dy dx, we have dy dt, the u being the x, dy du times du dx, but now in this case it's dy dx times dx dt. How is that helpful? We can solve for dy dx, which is what we'll actually be finding by division. And so we actually end up with how to take the derivative and find the slope of the tangent line, the normal slope of the tangent line, by deriving individually y of t and x of t.
Nice.
Now it gets a little more complicated when finding the second derivative. It gets a little more complicated when finding the second derivative, and possibly tomorrow with a little more time, which we will have,
Not tomorrow.
Monday, Lo Siento. To find the second derivative, basically, long story short, you have a first derivative. It's in terms of t. We're going to take that derivative of that first function in terms of t, but that poses a bit of a problem because if it was d dx, we'd be fine and have the second derivative of y with respect to x. However, we are unable to take it with respect to x because there are going to be t's in this whole thing. So in order to compensate, long story short, we'll talk about more y tomorrow, we're going to have to divide by yet another dx dt. We're going to have to divide by yet another dx dt. This is how we solve for derivatives of parametric functions. And let me go ahead and show it in practice. I have like a endeavor card or whatnot on the next page, but let's just go ahead and skip ahead to an example. Parametric, how do we know? X equals Y equals, has to be parametric. X equals Y equals. This allows us to have curved paths. Remember the orientation, all that jazz? Curved paths, because X needs to be a function of time and Y needs to be a function of time. Put them together, we'll have curves. If we need to find the second derivative of this function, we have to start by finding the first derivative of this function. And to find the first derivative of this function, we need to go ahead and, you guys saw the dy dt. The long story short of it is y prime over x prime. Something to memorize for sure. I will try to have all the endeavors ready for you guys to go on Monday so that we can write them down, get caught up, and then proceed. What's y prime going to be?
14.
Nice. Squared, because we bring down the 3, subtract 1. All over x prime, which is 2t. Can't we simplify a little bit?
Yes, pull
Yeah.
out.
Legally, we're gonna have a 2t squared, right? Minus a 3t, does that sound good? So we can pull t's out of the top and 2's out of the top.
So do you take the derivative of y? Oh, okay.
This is dy dx. But what they want is the second derivative. Do you see why I can't just do ddx of that thing? I can't do ddx, it all has t's. So how I'm going to go ahead and proceed is ddt of dy dx. Long story short, the variables aren't perfectly matching up. We have to compensate by yet another x prime of t, and this is actually how we could keep on going if we had to find more derivatives. So then we would end up with 4t minus 3 all over,
2t.
who is x prime? 2t. And if we want to find it at a certain point, t equals 1, we could go ahead and plug and chug. 4 minus 3 will be 1, 1 over 2 is 1/2. The slope of, I should say, the slope of the slope, the rate of the rate, the acceleration is equal to 1/2 at time equals 1 on my parametric curve. I'm dying. Just kidding.
It all makes sense now that you explain it.
Does it make sense how to solve it?
It
What's
makes
right?
more sense that you did that.
Yeah.
It was confusing when it was
Right? It
like
doesn't make sense before. You're like, what on
dt
earth? Why is there?
times dy dx over dx dt, but once you plug it in, it makes sense.
Yeah, and the problem is we can't do a ddx or else we're going to be in trouble, right?
Mhm.
Like, what do you do with that? But when we do ddt, we'll have it in terms of dt, but we need to divide by dx dt in order to be able to fully
Yeah.
reach our end.
Oh.
Now, there do come some dilemmas from parametric derivatives because there are questions that can come that can be a bit of a struggle. Like, and this is just pointing towards the AP because we have, how much time do we have?
Like
1 minute?
1 minute.
Okay. What if I was to ask you whether, this is more polar, but whether whatever particle is moving in this way defined by x and y, whether it was rising or falling at x equals 1, what would you have to do?
Check the
So
sign.
first,
Check the sign of not the first derivative,
Second.
second derivative?
not the second derivative,
Third.
of only y prime. How come?
Huh? Oh.
Why only y prime and not y prime over x prime? If it's rising or falling, we're only talking about what kind of motion?
Upward.
Vertical, so y prime. If I'm talking about to the right or to the left, I'm talking specifically only about x prime. Does that make sense? So a few of the questions as far as like long answers and FRQs and stuff is going to get a little bit funny in a sense of maybe how we refer to things that we've learned in the past, but it also applies to work.
If they
So
want,
kiddos, take this homework, try to finish it up by Monday. And we'll hash it out.
if they want to find out like the like how is it the if it's not going just up or down, it's going diagonally.
They would just be referring to dy dx.
So okay, but
Because you're talking about the horizontal and the
And-
vertical together.
yeah,
That'd be the slope of the tangent line, which is dy dx.
it would be that. But what do you plug that into? How do you just plug it in T and be like, oh, this is the
Well, if they're
slope.
asking at a certain time what's going on, or if they're asking when it's positive or negative, you could
oh,
say
you
it's
just plug
greater
in
than.
T. I thought you like that was like a okay.
The symbol believes everything comes, but the theory gives thought to its steps.
Yes.
Proper working